Thank you for that introduction, Bob. So my role on this panel today is to provide you with a little perspective from the point of view of a geologist, because there are a lot of people in this room who think about the oceans, but I think about the oceans probably on longer timescales than most of the people in this room. So my area of research is to look at sea level rise, which indeed is very topical in the state of Florida. And I look at past sea level changes, and in particular, I want to understand how sensitive ice sheets are to changes in temperature. So I often get the question, well, how relevant is this work that you're doing that looks at sea level change over thousands of years? How is that relevant to understanding how sea level rise is going to play out in the next few decades? Because that's what we want to know. We heard about that this morning. And that's a perfectly valid question, right? So ultimately, my goal here today is to help you to understand why geologic timescales are indeed very important to discussions on policy that relate to how we interact with our oceans, on human timescales, and indeed even on political cycles. So let's think about the sea level rise example again. I'm sure you've all had this experience, you go to get yourself a cold drink, you drop an ice cube on the floor, and it starts to melt, and you come back and you find a puddle of water. It'll probably melt pretty fast in this room today, right? So let's now think about the ice sheets of Greenland and Antarctica. We've effectively thrown them into the hot room, and you'll see some of that melt right away. But that action of throwing them into the hot room has long-term consequences. People talk about sea level rise the year 2100. It's going to keep rising after 2100. And we may be committing ourselves to something that will play out over many thousands of years. And that's the perspective that we need as we approach these policy issues. But I'm not here today to talk about sea level rise. I couldn't help myself but do just a little bit. But I've been asked to talk to you on this topic, the resiliency of the oceans. And to be honest, when they asked me to speak about this, I was a little bit worried because, as Rob mentioned this morning, resiliency, I don't want you to walk out of here thinking that the oceans are resilient. We can throw anything at them, everything's fine, right? I mean, it's true. The oceans will still be there. So I spent a lot of time thinking about what this phrase meant to me. So what you see in the box here is kind of my working definition of the resiliency of the oceans. The capacity of the oceans to adapt and adjust to forces of change and to become strong and healthy and successful again, right? And there are three components to this that you'll see are overarching themes that will occur throughout this talk. One is that this may involve some type of transformation, a permanent transformation. Another is that there are mechanisms for adaptation that will come into play. And the third is that the rates of change of this adaptation are really critical in determining the overall resiliency of the oceans, right? So this is not the first thing that comes to mind when people think of resiliency, right? So in fact, I Googled the definition of resiliency, and this is the first thing that comes up. It says resiliency is a quality in objects to hold or recover their shape, or in people to stay intact. This is a kind of strength. If you bend a fork and it bends right back, that's resiliency, right? So I had this image of my son, who's 5 years old, flinging a fork of mashed potatoes in my daughter's face, and the fork goes right back. That's not the resiliency of the oceans. It will not necessarily snap right back to the condition it was at before, right? So this completely misses the mark for me. So I went to the Merriam-Webster dictionary, more trusted source for me, and they defined it as the ability to become strong and healthy. I like this part of the definition. This captures the concept that there may be some adaptation here, there may be some transformation. It doesn't necessarily go back to the same state. But the key message is that that adaptation may take time. So the rates of change are really important. So if you go to the OED, their definition is the capacity to recover quickly from difficulties. Right? The ocean is big, it is vast, it is deep, it is largely unexplored, right? Not only because of its physical size, but because of the processes involved, this adaptation may take time, and this is an important thing for us to remember. So before, I'm going to show you a few examples from the geologic past to show you what we understand about the resilience of the oceans, and what these timescales of response are, and how that recovery happens. But I want you to keep this in the back of your mind as we go throughout this. There's a lot of talk these days about something that's called the food, water, energy nexus, right? This is an emerging issue across the globe. And how our access to these critical resources plays out is going to be heavily influenced by the future development of what I would like to call the ocean atmosphere climate nexus, right? And rapid changes in this dynamic system will threaten the safety and security of these food, water, and energy resources. And the ocean is a huge player in that, literally and figuratively, right? So keep this in mind. All right, so first stop in our time machine is going to be go back to the late Cretaceous. And this artist's illustration of the late Cretaceous ocean shows that the oceans were teeming with life. But if I had to pick someone out of the room and ask you to name some of these different organisms you see in this picture, you might be hard-pressed to do so. These were very successful organisms. They existed for millions of years. We have them in the fossil record. We can see they were very successful. Yet very few of them are around today. Not just because there's been time and evolution in between, but because of something that happened at the late Cretaceous. And this is not just a nice little shooting star up in the sky that you see in this picture. I know a lot of you know part of this story is that at the end of the Cretaceous, and famously perhaps causing the extinction of the dinosaurs, something rather cataclysmic happened. An asteroid more than 10 kilometers across, that's more than 6 miles wide, slammed into the Earth at an angle about 20 to 30 degrees at a site known as Chicxulub, raining down ejecta across the entire globe, right? And causing a mass extinction, the 4th largest that we have in the geologic record. So this caused a nuclear winter. It caused collapse of productivity of the oceans, people think, ocean acidification, all kinds of, there are lots of ways to die at the KT boundary. Right? This was truly a bad weekend on planet Earth. So this crater, actually next month, the International Ocean Discovery Program is going to be drilling into this crater to understand more about the impact and also what happened in the aftermath of it. This crater, as shown here in this gravity map, is almost 200 miles wide. It's at the site of what is now the tip of the Yucatan Peninsula. And when it slammed into Earth, it released an energy equivalent of 8 million thermonuclear weapons, or about 2 million times more powerful than a hydrogen bomb, right? That's pretty devastating. Yet not all impacts in geologic record are associated with a mass extinction event. There are extinctions, but not one like this. And there's a reason for that. Because a couple 100,000 years before, a mere blink in the geologist's eye, this started to happen. The eruption of the Deccan Traps, which are flood basalts that cover a huge portion of India, a massive volume of lava outpouring from here, emitting volcanic gases, including carbon dioxide, that would have heated up, and lots of other noxious volcanic acids that would have been absorbed by the oceans and caused environmental stress not only in the oceans, but also on land. So we're looking at stressed ecosystems, both on land and in the oceans. And it was at this point when that asteroid hit, right? And I'd like to share with you some new data that I've helped to just generate from a site in Antarctica where we have a temperature record that's shown in the green curve there. And that temperature record shows a late Cretaceous cooling that's well documented across the globe. But we have a nice expanded section across the boundary here. And we can see that right at the time when the Deccan Trap starts erupting, we have a massive spike in temperature and an extinction event that is equivalent in size at this site to the extinction event that occurs at the actual boundary when the asteroid hit, right? So what we're looking at is an ecosystem that was already stressed, and it was this 1-2 punch that really wiped things out. So what was the response of the oceans? More than 75% of marine organisms went extinct, not to mention all the ones that died, as maybe they didn't completely go extinct. This 1-2 punch story really tells us that a vulnerable ecosystem is more susceptible to collapse. And this is a very relevant lesson when we're thinking about current policies for the ocean. The other thing that we've learned by all these sediment records that are taken from marine sediment cores in the deep ocean by the IODP, ranging from sites in the Caribbean over to the Pacific, here at Shatsky Rise, one that I helped to describe here many years ago. I like to point out that I'm the only person in this picture actually doing any work. And that is the KT boundary section core that they're looking at, which is why they're all pondering it like this. I mean, it's a truly devastating event in Earth history. But that recovery that we see took millions of years. The time period after this is very low sedimentation rates in the oceans around the world globally, right? It took a long time for this recovery to occur. So let's fast forward about 10 million years to the Paleocene-Eocene boundary, about 55 million years ago. An event occurred at this boundary known as the Paleocene-Eocene thermal maximum, but because that is a mouthful, we call it PETM for short. And what happened here, you can see even to the untrained eye, is very dramatic. So here's a core from the South Atlantic, from Walvis Ridge, where you see all this white sediment comes from carbonate, calcium carbonate from shells of marine organisms that rain out on the sea floor. And at the PTM, that carbonate disappears. What happened is we had an abrupt pulse of CO2 into the atmosphere. It got absorbed by the oceans, that became acidic, and then dissolved that carbonate sediment away in the deep sea. So what was the ocean response? We had ocean acidification, a spike in temperatures globally, an extinction event in the deep sea, which is how this boundary was first defined, in fact, a very widespread extinction event. And the recovery in this case took several hundred thousands of years to occur. And this is a very an interesting example for us to think about. But you can see here, here's the whole core again, and you can see the PTM very clearly. This was a dramatic event. And we know from coring at different depths in the ocean at Walvis Ridge here, which is what is shown, this is what tells us that the recovery actually happened faster in the surface of the ocean than it did in the deep ocean, which kind of carries on from one of the themes that we heard this morning. So this is an interesting example for us to think about in the context of what's happening today. Pulse of CO2, ocean acidification, warming, all of those things that we have in common with our changing climate. The difference is that at the PTM, that CO2 is emitted to the atmosphere much more slowly, right? But still this example tells us something about the recovery times involved when an event like this happens. And so that we know it may take hundreds of thousands of years to recover from the actions that we have on short time scales. All right, so if we come back to this definition of resiliency of the oceans again, we can see from these examples in the geologic record that the oceans can adapt. They have the capacity to become strong and healthy again. But because the timescales of response operate over thousands to millions of years, large and abrupt perturbations to this system can lead to irreversible transformations of marine life, which has a cascading effect on other aspects of the system, such as sedimentation, chemistry of the seawater, and so forth. So even if a certain amount of change is going to be inevitable for us, slowing down those rates of change can enable some natural compensation to occur, relying on the natural resiliency of the oceans. So our actions can set processes into motion that occur over these long timescales to play out. That will effectively commit the ocean and indeed the whole Earth system to a certain pathway, where at least certain elements along that pathway may be irreversible. Thank you for your attention.